So far, we have learned two major methods for solving differential equations: linear differential equations and separable differential equations. But most differential equations do not fit into either of these categories. We will learn one more method for solving a specific type of first-order differential equations called exact equations. For others, we will need to find numerical approximations for solutions using methods such as Euler's method. Let's start by looking at an example that we cannot solve using our current methods. Here, we'll solve the differential equation 3x squared plus y squared plus 2xy times dy dx equals 0. We can see that this is not linear due to the y squared term, and this is also not separable because we can't write it as a function of x times a function of y equal to dy dx. So our current methods fail. While it's very difficult to spot, and we'll learn later how to spot it, we can verify that the function psi of xy equal to x cubed plus x times y squared has the property that the partial derivatives play a defining role in our differential equation. What I mean by that in particular is that the partial derivative of psi with respect to x equal to 3x squared plus y squared, and the partial derivative of psi with respect to y equal to 2xy are used to build our differential equation 3x squared plus y squared plus 2xy times dy dx equals 0. And since psi is a function of x and y is a function of x, the function psi of xy is really just a function of x. Thus, we can compute the derivative of psi with respect to x. Using the chain rule from multivariable calc, we get that the derivative of psi with respect to x is the partial derivative of psi with respect to x plus the partial derivative of psi with respect to y times dy dx. That is, the derivative of psi with respect to x is psi sub x plus psi sub y times dy dx. But using the psi that we have above, this is 3x squared plus y squared plus 2xy times dy dx, the left-hand side of our differential equation. And from the differential equation, we have that this is equal to 0. So we get that the derivative of psi with respect to x is equal to 0. And integrating both sides of the derivative of psi with respect to x equal to 0 with respect to x yields that psi is equal to a constant, c. On the other hand, psi is equal to x cubed plus x times y squared. So values of x and y that satisfy the differential equation also satisfy x cubed plus x times y squared equals a constant c. And this gives us an implicit solution, x cubed plus x times y squared equals c, to the differential equation. So we were able to find an implicit solution, x cubed plus x times y squared equals c, to the differential equation 3x squared plus y squared plus 2xy times dy dx equals 0, because we were given this psi equal to x cubed plus x times y squared, such that psi x equals 3x squared plus y squared and psi y equals 2xy. And this process can be repeated so long as we can find such a psi. In general, a differential equation of the form m of xy plus n of xy times dy dx equals 0, such that m of xy is equal to psi sub x and n of xy is equal to psi sub y for some function psi, is called an exact equation. And the implicit solution of this differential equation is psi of xy equals c, as we saw in the last example. But what if we weren't given such a psi as we were in that last example? How could we tell if such a psi exists? And if psi exists, how can we find it? To answer the first question, recall from Calc 3 that if psi of xy is twice differentiable, then the mixed partials are equal. That is, If we first take the derivative of psi with respect to x and then with respect to y, it's equal to the partial derivative of psi with respect to y, then with respect to x. So if such a psi exists that m equals psi sub x and n equals psi sub y, then the partial derivative of m with respect to y, which is psi sub xy, is equal to psi sub yx, which is the partial derivative of n with respect to x, n sub x. So we can conclude that if m of xy plus n of xy times dy dx equals 0 is exact, then m sub y is equal to n sub x. But what if m sub y is equal to n sub x? Can we make the conclusion the other way? Can we then say if m sub y is equal to n sub x, then m of xy plus n of xy times dy dx equals 0 is an exact equation? To verify this, let's look at the differential equation m of xy plus n of xy times dy dx equals 0 and suppose that m sub y is equal to n sub x. The way that we will show that this differential equation is in fact exact, so long as m sub y is equal to n sub x, is that we will construct a function psi such that psi sub x is m and psi sub y is n, therefore allowing us to conclude that it is exact. Now, to ensure that psi sub x equals m, we can integrate m with respect to x to get psi. It'll give us psi of xy equals the integral of m of xy dx, where we'll fix y as a constant and integrate with respect to x. This will determine psi of xy up to a constant with respect to x. But remember, any function of y is constant with respect to x. That is, we can write psi of xy as psi of xy equals q of xy, the integral of m with respect to x, plus h of y, a function of y that is constant with respect to x. And to determine the constant with respect to x, which is hy, we will take the partial derivative with respect to y to get that psi sub y is equal to q sub y plus h prime of y. But on the other hand, psi sub y is equal to n of xy, giving us that n of xy is equal to q sub y plus h prime of y. Or rearranging, h prime of y is equal to n of xy minus q sub y. And finally, to find h prime of y and thus know psi, we can integrate the right-hand side with respect to y, which will give us psi up to a constant c. And since we can find such a psi, so that psi sub x is m and psi sub y is n, we can conclude that this differential equation is in fact exact. Moreover, the way this proof works is that we actually construct the function psi of xy, meaning that by following this process, we also find the solution psi of xy equal to c for the differential equation. I'd like to note that to do the last integration, we need n of xy minus q of xy to be a function of just y. We can see this is true by showing the partial derivative with respect to x is 0. This is where we'll use the assumption that m sub y is equal to n sub x. Though we'll leave the proof out of this video.